Currently, most schools and even universities are banning students from using AI. The reason is that many schools and teachers don't know how to incorporate AI into education. But it's clear that AI is very important for both students and teachers alike. The education system in any country is the most conservative system, and it's hard to change. As AI evolves very quickly, we can't wait for a new education system to be implemented, or we'll find ourselves unprepared, with nothing to do when we graduate from university. The OpenAI O1 reasoning model was just released last week, and its capabilities can surpass most Ph.D. holders. We must adopt a different approach to learning. The key skill you need now is the ability to lead an AI employee with Ph.D. level expertise. Our target audience consists of people with no prior knowledge of coding or AI, particularly those who are currently attending university but not studying computer science, or those who are studying it right now. We believe we can condense an entire university-level computer science curriculum into just about 25 sessions. In 6 to 12 months, you can master the key concepts that usually take 4 years to learn in a traditional university setting. While universities traditionally teach you the skills to find a job as an employee, today we'll give you the skills to manage a PhD-level AI employee. That's all you need to learn moving forward. But remember, when we say 6 to 12 months, this isn't just about watching videos or attending a live class once a week. Each week we'll have a session, and after watching the video, you'll need to complete the assignments, practice, and even do some homework. If you do this, we guarantee that you will acquire all the skills you need. In this session, you'll not only learn the most important concepts of computers and Linux, but you'll also learn how to use AI to build a remote cloud server monitoring system. Even if you have no coding experience and are just starting today, I will guide you through the process of building a cloud server monitoring system with AI. This is completely different from traditional computer science education. In a traditional coding class, you may not be able to build a cloud server monitoring system even after completing a 4-year course. But today, with AI, we approach learning differently. Since we're learning coding and computers, it's important to understand that computers and Linux are critical. Just like in university, we won't only focus on coding, but also on all the knowledge you need to create a project and build a product. Okay, let's continue. First question. Why are we learning coding? Learning to code is actually a huge task. We aim for you to become a full-stack developer by guiding an AI employee after 6 months. But it's not as simple as that. It's a big task. So how do we simplify it? We apply the first principle rule. What's the first principle? It means breaking down a big, complex task into smaller, manageable pieces, making it easier to understand. Once you break it down, you can go step by step, making everything simpler. Now let's think about it. Why do we learn coding? What's the purpose? It's important to understand that learning to code isn't just about finding a job. You could find a job doing other things without coding. Learning to code means you're aiming to build something. Maybe you want to create a website, or perhaps a mobile app. Or you might be interested in working on a smart home security system, like a security camera. Maybe you're working with embedded devices, like a motion sensor, where if someone enters your home, it triggers an alarm by detecting the motion. Or perhaps you're looking to build an automation system for an electric car, which is largely driven by software. Maybe you want to build an AI robot or a large language model app. Or maybe you just want to develop applications for Windows, Linux, or Mac. So ask yourself, why are you learning coding today? That's the most important question. But here's the thing. Thanks to AI, with its assistance, you can do almost anything. In our course, we don't just teach you how to build a website, a robot, or an application for a specific device. We teach you how to become a full-stack developer with AI's assistance. And what does that mean? It means that with the help of AI, you'll be able to build anything you want. You can develop any kind of software. So our course is similar to a university setting. At university, they teach you a broad range of things because they don't know what you'll do after you graduate. In our course, we compress the entire university curriculum and teach you everything you need to know with AI. Once you learn these things, you'll be able to do whatever you want right away. We don't focus on any one specific task. We focus on everything you might need or want to do. Because we want to code, we need to think about our development environment or platform, Windows, Linux, or Mac. When you build any software, you must test from time to time during the whole software development lifecycle. Developing and testing on the same platform is the most efficient way. However, in reality, that's not often the case. Most of the time, the final software will run on a different platform than the one you developed on. It could be on a smartphone, like Android, iOS, or some other system. It might even run on an embedded smart home device, or even a single-chip MCU. MCU stands for Microcontroller Unit, which is a very small computer on a single integrated circuit. But what can we do? If we can't find the exact same platform for development and testing, can we still have a similar environment? So let's help you make the right choice for both your development and testing platforms. Our choice would be Linux. But why Linux? Let me explain. Most cloud servers use Linux as their operating system. Most software you develop may need to run on a Linux cloud server. Android, iOS, and even Mac computers are all based on Linux, or very similar to it. Most embedded devices like TV boxes, Wi-Fi routers, security cameras, drones, robotic systems, and servers all run on Linux. This means that when you use Linux for development, the concepts, knowledge, and coding are almost the same as your software's target platform or environment. You can write the code on Linux, then compile and test it on Linux as well. In most cases, the same code doesn't need any modification, or just very little adjustment to be compiled and run on other platforms directly. Also, almost any platform provides a cross-compile toolchain for Linux development, a set of tools that allows developers to compile code on one platform that will run on different platforms. Another advantage is that Linux is open source. What does open source mean? It means that if you encounter any issues, you can check the source code of Linux. Since it's open source, AI has learned all the source code of Linux. AI has more knowledge of Linux, and AI can more efficiently help you write code, analyze, and troubleshoot. In contrast, if you're developing for Windows, since Windows is not open source, AI hasn't had the chance to learn its source code, which limits its ability to help. So here's a common question. Most students use Windows. So what can you do if you don't have a Linux machine? It's actually quite simple. Most developers may like to install Ubuntu Desktop, which is Linux, alongside Windows as a dual OS system. Microsoft also feels Linux is too important to developers, and they don't want developers to use an independent Linux. So they've developed a software called Windows Subsystem for Linux, WSL, which allows you to run a full Linux shell or command line environment directly on your Windows PC. The latest version is number 2, so we mostly call it WSL2. So installing WSL2 is another lightweight solution. Alternatively, you can install VMware, VirtualBox, or even use Cygwin to emulate a Linux environment on your Windows machine. But I highly suggest you install Docker, a virtual development container software. You can develop locally with a Docker container, and you can even directly push the same container to your remote cloud server for deployment. I'll guide you to learn more about how to use Docker for development in my upcoming videos. If you prefer not to install anything locally, or it's hard to install these features in the beginning, or even if you don't have a computer right now, you can use a cloud-based Linux development container, a more modern way for development. First, I highly recommend GitHub Codespaces, which offers a free cloud container for development. If you sign up with a student email address, you can get even more free usage. This means you don't need a computer. You can access the cloud development container and use it whenever you need. Another great option is Junior IT's cloud container, which is based on Docker containers, making it even easier. So you don't need to worry if you don't have a Linux machine or even a computer. You can still learn and develop on Linux without any issues. However, if you have a Windows machine, I would recommend installing Docker locally. This will give you more flexibility for learning and development. The next question: what is an operating system? We've talked about Windows and we've talked about Linux. Both of these are examples of operating systems. But what exactly is an operating system? An operating system is a software that acts as an intermediary between the computer hardware and the user. It's what allows you to interact with the hardware, to do things like play games, watch videos, or run software. You can't just use the hardware directly to perform these tasks. You need software to help you do that. In theory, you could build software directly with binary code from the hardware level, but in most cases, we don't need to do so. We have the operating system, which can't only be used by humans, but can be used by your software too. Only when developing software for some embedded devices, many of them might not have an operating system. In those cases, you might need to write the code from scratch. But don't worry, it's usually a simple function, and the code might not be more than 200 to 300 lines. The operating system makes it easier for both humans and software to interact with the hardware of a computer. So what is the hardware of a computer? Let's think about it. What exactly is hardware? Most of you are probably familiar with some aspects of computer hardware. You've heard of the CPU, right? You know how powerful it is, or how much memory your computer has, or how much storage it has. Many of you might be using laptops, so these things are already familiar to you. Today, it's easier to understand these concepts because most people have a computer. But as developers, we need to think a bit differently. One important concept I want to introduce is the von Neumann architecture. This concept, which is the foundation of modern computers, was first described by John von Neumann in 1945. At that time, computers as we know them today didn't even exist. It was just a concept. But the computers we use today are all based on this architecture. So what does this architecture involve? The first part is the processing unit, which is responsible for calculations. Computers are designed to perform arithmetic and logic operations. But how do they know what to calculate? That's where the control unit comes in. It controls the process of computation, making sure the right calculations are done at the right time. Together, the processing unit and the control unit form the CPU, which is the core of the hardware. Another important part is memory. Memory isn't just about how much RAM your computer has. It's the location where your code instructions and data are stored during the calculation. Von Neumann was a genius. He invented the most important concept: store the code instructions and data in memory, not in the CPU. Obviously, memory is much cheaper than the CPU today. It can store much more code instructions and data, which lets the CPU do more complex tasks and keep the cost lower. For example, your computer memory can easily be upgraded from 8 GB to 16 GB or 32 GB. but it's almost impossible to upgrade the CPU. Let's think and understand this in another way. You can think of the CPU as your brain, and the memory as a library full of books. It's impossible to store all the information in your brain at once, right? So when you need information, you go to the library, pick up a book and read it, and bring it to your brain to process. Once you've finished thinking, you might write down your results on paper, just like how the CPU writes data back to memory. This concept is very important and fundamental to coding and development. So how do CPU and memory work together? Let me show you a simple example and introduce an assembler simulator to help explain this process. Assembly is a low-level machine instruction language that can be interpreted directly by the CPU. Since different CPUs have their own unique assembly instruction sets, it's common to learn assembly using a simulator. This makes it easier to understand assembly concepts without being tied to a specific CPU. Once you need to write assembly for a particular CPU, you just need to refer to that CPU's instruction set, as the core concepts remain the same. The assembler simulator is an 8-bit CPU simulation that mimics the x8086 CPU, which is part of the well-known x86 architecture. This architecture is used most in Windows and Linux computers, in contrast to the ARM architecture, which is often commonly used in Android, iOS devices, and the latest MacBook computers. CPU architecture generally refers to the instructions set architecture, which defines the set of instructions a CPU can execute. Before the development of standardized architectures, creating a new CPU model required rewriting software to be compatible with the new hardware. With the introduction of instruction set architecture, software can run on different CPU models that share the same architecture without needing to be rewritten for each model. Now let's see how the CPU and memory work together, step by step. At the top right of the simulator, you can see several CPU registers. These are high-speed storage units that act as the CPU's temporary memory. At the bottom right is the main memory, which functions similar to your computer's DDR memory. These registers allow the CPU to quickly access instructions and data from the main memory, and then process them much faster than if it were to access memory directly. As we run the code step by step, you'll see how the CPU reads instructions from memory, performs calculations, and then writes the results back to memory. This process happens in cycles. First, the CPU reads the data, then processes it, and finally stores the result. This is how all computers operate, and this cycle occurs millions of times per second. Now, let's briefly talk about another important component of modern computers, the GPU, Graphics Processing Unit. While the CPU is designed to handle a wide variety of tasks sequentially, the GPU is built for parallel processing, enabling it to process large amounts of data simultaneously. The GPU has many more registers than the CPU because it handles thousands of threads concurrently, especially in tasks like rendering graphics, AI, and machine learning. A modern CPU typically has around 16 to 32 general-purpose registers, while a modern GPU can have tens of thousands of registers distributed across its many cores to support massive parallel workloads. The CPU does not have dedicated internal memory. Instead, it relies on external system memory, RAM, for its operations. In contrast, the GPU has its own internal memory, known as video RAM. This memory is much faster than the typical system RAM, allowing the GPU to effectively process large amounts of graphical data or AI models for tasks like training and inference. Unlike the von Neumann architecture used by CPUs, where instructions and data are processed sequentially, the GPU can store and process both instructions and data in parallel. This architecture enables the GPU to handle tasks such as graphics, rendering, and AI-related computations much more efficiently. Let's dive into input and output, two fundamental concepts in computing. They're quite simple to understand, but essential for how we interact with computers. Input refers to devices like keyboards, mice, touchscreens, microphones, and even sensors. These devices allow humans or the physical world to provide instructions or data to the computer. For example, when you type on a keyboard or tap on a touchscreen, you're sending input to the computer. Output is how the computer responds and communicates with humans or the physical world. Common output devices include monitors, speakers, printers, and LEDs. For instance, the words you see on your screen or the sound you hear from your speakers are examples of output. In simple terms, input and output devices form the bridge between the computer and the user or the physical world. Without them, we wouldn't be able to interact with or perceive what the computer is doing. Next, let's explore the different ways developers and regular users think about hardware. As a developer, you can't think the same way non-technical users think about the hardware of a computer. For example, when regular users think about a CPU, they might only care about how fast it is. But as a developer, you need to understand how the CPU works, how it interacts with memory, and how it processes instructions. When it comes to memory, non-technical users often focus on how much RAM a computer has. However, as a developer, you need to think about memory allocation and how to manage resources efficiently, especially for systems with limited memory, like embedded devices or microcontrollers. Now, let's talk about disk, which is important for both developers and users. While users focus on disk space for storing and managing files, developers need to consider disk management more deeply. This includes ensuring efficient read-write operations, optimizing performance, and planning for data recovery when necessary. For input and output devices, regular users might care about things like screen size or resolution. But as a developer, especially if you're involved in hardware or software design, you need to dive deeper. Even something as simple as a mouse requires software to control its behavior, and designing that software involves understanding the technical details. Overall, most users think of input and output devices like consumer electronics, focusing on performance and cost. However, developers need to have a deeper understanding of how these devices interact with the system to ensure everything runs smoothly. Let's talk about DOS, or the Disk Operating System. DOS, specifically the well-known version called MS-DOS designed by Microsoft, was an early operating system, primarily used before Windows became popular. It was designed to manage files, directories, and basic hardware interactions through a command line interface. Back in the early days of computing, there were no graphical user interfaces, just a simple terminal where you interacted with the computer by typing commands. Everything was text-based. Using a computer meant learning how to save files, create directories, and delete them, all through DOS. At that time, the primary focus was on managing disks and files. Today, operating systems have evolved into a much more complex system. For example, on your smartphone, whether it's Android or iOS, you primarily interact with apps. The apps handle everything behind the scenes. If you run out of storage, you simply upgrade your storage or get a new phone. You no longer interact with files and directories as directly as you would on a traditional computer. However, for developers and professional users today, understanding how to manage files and directories is still essential. On a computer, whether for work or personal projects, you need to organize files and folders, knowing exactly where your data is stored. If you use Windows, you've probably noticed that the main drive is labeled C. But why does it start with C? This dates back to the early days of computing, when A and B drives were reserved for floppy disks. The A drive was typically used for the operating system, and the B drive was used for data storage. When hard drives were introduced, they were assigned to the letter C. Some software even hard-coded file paths to the C drive. So, to manage compatibility with older software and systems, the tradition of starting with C for the main drive continues today, even though floppy drives aren't used anymore. In contrast, Linux handles drives differently. If you're used to Windows, you might wonder, where's the C drive? In Linux, there's no C drive. Instead, everything starts from the root directory, symboled by a /. All files and directories are organized under this root structure. Even the hardware is treated as files under the /dev directory. This is a different way of managing storage and hardware compared to Windows. Why is the super admin called root on Linux? In Linux, the file system is structured like a tree, with the root represented by a single /. All files and directories start from this root. In Linux, everything is treated as a file. Files, folders, and even hardware devices like USBs, keyboards, GPIOs, and CPUs are all represented as files. What is a GPIO? It stands for General Purpose Input-Output. We'll learn more about it later, but for now, think of it as a way to connect simple devices like switches or LEDs directly to the CPU. With GPIOs, you can control the CPU to turn your LEDs on or off. These hardware devices are located in the /dev directory in Linux. Hard disk drives, SSDs, logical disk partitions, and folders are connected to the Linux file system tree through a process called mounting. Mounting attaches these devices to specific locations in the file using the mount command. For example, when you mount a hard drive or USB stick, it becomes accessible under the file system, such as in /mount/USB. Now, let's talk about super admin privileges. The administrator in Linux is called the root user. The root user has complete access to the entire file system, starting from the root directory. Other users, however, are typically restricted to specific parts of the system, like the home directory, which serves as a safe boundary for their activities. A specific command called chroot, short for change root, can be used to restrict users to certain areas of the file system. The chroot command changes the root directory for a user to a specific directory. For example, in a shared web environment, a user's root directory would be changed to their website's directory. This is often referred to as a jail file system because it prevents users from interacting with or even seeing other users' files, particularly sensitive files like those for other websites. The concept of chroot or a jail was critical for shared environments before virtual machines and Docker got popular. Since Linux is widely used across various environments, including servers and cloud systems, many of these systems operate remotely rather than being physically in front of you. When your computer is on your desk, you can easily keep an eye on CPU and memory usage. But with a cloud computer, things are different. If your CPU usage spikes or memory starts filling up, it can lead to serious issues, potentially causing an outage of your cloud service. If you're running a database, for example, disk space can fill up fast. Once the disk is full, it might switch to read-only mode, which can cause major disruptions. You also need to keep an eye on network health. If your network connection drops, users won't be able to reach your server. That's why monitoring 4 key resources is essential for cloud computers: CPU usage, memory usage, disk space, and network health. On Linux, there are several commands you can use to monitor system resources. For example, top, free, df, ping, etc. These command names might seem unfamiliar if you're new to Linux, but they're incredibly powerful. You don't need to memorize them all. Just focus on what you need to monitor: CPU, memory, disk, and network. Whenever you need help, you can rely on AI assistants to guide you through learning or recalling these commands. Manually monitoring your cloud server constantly is not practical and often impossible, as you can't keep an eye on your server 24/7. That's where a monitoring system becomes essential. You can set up automated monitoring to track your server's performance and configure alerts to notify you via email or other channels whenever there's an issue with CPU, memory, disk space, or network connectivity. After watching this video, join the Junior IT Discord server using the link in the video description, where you'll receive an assignment to use AI assistants in building a cloud server monitoring system. You'll also learn how to set up an alert system that automatically notifies you when something goes wrong, so you won't have to manually check your server constantly. The best part? You don't need to know how to code. As long as you understand the core concepts, our ByteBoss AI agent will guide you in building the monitoring system. If you enjoyed this video, please subscribe to my channel to stay updated on the latest content. See you next time!